Okay, in this video I was going to do just a couple more problems related to exponential growth and decay. We were going through a worksheet here and I was just kind of picking out selected problems to work through together. We did a few of those in the last video, and so I was just going to do a few more here. Another problem that I had liked was problem 10. I was just going to have us do part A in problem 10. Parts B and C are going to be pretty similar to what you see there that I'll be doing in part A. So let's take a look at that. It says in problem 10, according to Newton's law of cooling, the temperature, F of T, of a heated object decreases exponentially over time towards the temperature of the surrounding medium, which we'll call capital T. The temperature, F of T, can be modeled by the function, which is given here. C and K are constants. Also, T is a constant in the formula. All right, let's take a look at part A, where it says a piece of metal is heated to 300 degrees Celsius and then is placed in a cooling liquid at 50 degrees Celsius. After 4 minutes, the metal has cooled down to 175 degrees Celsius. Find the temperature after 12 minutes, and there's a note here, we're going to change minutes to hours. Okay, now of course in this problem we have exponential decay, right? This hot piece of metal is placed in a cooling liquid, so obviously as time goes on, the temperature, F of T, is gonna decrease, right? So it makes sense why we want that power to be a negative, since that temperature is going to be decreasing over time. All right, so here's the function that was given to us. Now T is the temperature of the surrounding medium, they say, or think of it as the temperature of the new environment. Okay, so this hot piece of metal is being placed in a cooling liquid that is 50 degrees Celsius. That is the new environment. So T, therefore, would be 50 degrees Celsius. Okay, and here's the function then that I currently have. Now, at time 0, before the metal goes into the cooling liquid, it is 300 degrees Celsius. All right, little t is the temperature, little t is the time. So at time 0, like I said, the temperature is 300 degrees Celsius. Now at time 0, that would also mean that I plug 0 into the formula for where I see little t. 50 plus c times e to the negative k times 0. Anything to the 0 power is always 1. So you're going to have 50 plus c times 1, or 50 plus c. And if you subtract 50 from both sides, you get c to be 250. Okay, so essentially we're looking at the fact that c is 250 here. Okay. Now, before I find out what's happening after 12 minutes, okay, I need to finish getting the constants that are specific to this problem here. I've already got T and C identified. The last thing would be to get the K value. Well, they had said that after 4 minutes have gone by, the metal had cooled down to 175 degrees Celsius. It also said that you're going to change minutes to hours. So there's 60 minutes in an hour. 4 minutes out of 60 minutes would be the same as 1 over 15. Since 4 goes into 60 15 times. So if I plug in 1/15, that is essentially saying that I'm looking at the temperature of the metal at 4 minutes, which again is 175 degrees Celsius. Also, if I plug in 1/15 into the function, this is a function of time t, so I'd be plugging that into the formula here where I see t. And let's solve this equation for K. All right. If we subtract 50 and divide by 250, 125 divided by 250 is 1/2. And then, now the bases are not going to match up nicely there, so I'll want to take the ln of both sides. That will allow me to bring the power in front of the logarithm on the right. So on the right, you're going to have negative 1/15 K times the ln of E. The ln of E is 1. And then to get K all alone, you're going to multiply both sides by negative 15. Negative 15 times the ln of 1/2 I think I miswrote that. Negative 15 times the ln of 1/2 is roughly 10.397. Okay. Now, k is a negative, right? So I need to make sure that I'm still using writing this as a negative exponent since the temperature of the metal is decreasing over time. Now, here's the formula that represents the situation. Okay. Now that I've got the function specific to this problem, I can then be able to know the temperature of the metal at 12 minutes or at any other time. Of course, it's going to be less than 175 degrees Celsius, right? Because at 4 minutes, it's at 175 degrees, and it's going to continue to cool down. So I should expect my answer to be something that is less than 175 here. Again, you're going to change minutes to hours. So 12 minutes would be 1/5 of an hour, since 12 times 5 is 60 minutes. So if I want to know what's happening at 12 minutes, I'm going to want to plug 1/5 into the function. Well, I've done that. And so then I'm going to go to the calculator and type this in. If you type in what we have here and hit enter, I was getting roughly 81.25 if you go nearest 2 digits. Okay, and of course the units are in degrees Celsius, so you'd want to indicate that so that it's not going to be confused with degrees Fahrenheit. All right, and so that would be the temperature of the metal at 12 minutes then. And of course it's going to continue to cool down and approach a temperature of 50 degrees then, since that's what the cooling liquid had a temperature of. Now, typically in these Newton law of cooling problems, there's a bunch of preliminary work that needs to be done in getting the constants. That's what I'm doing up here. Okay, and that's typical, by the way, since you're really creating a function that is specific to that problem. And once you've got that function figured out here, then you can be able to plug in, other numbers. So something to keep in mind. Okay, now all the problems that I've been showing you on the sheet here, the selected ones, have all been exponential decay problems. So I thought we'd maybe look at a couple of exponential growth problems. I wanted to look at maybe just 2 more and then call it good. Problem 11 was a problem I liked. Let's take a look at that. It says the population, P, of a colony of mosquitoes at time t, which is in days, obeys the law of uninhibited growth according to the function P of t. Notice how this is representing population growth, right? The exponent is a positive, so as time goes on, there's going to be more mosquitoes in the in the population there. Okay. Now I would like us to find the population after 3 days. So, well, t is the time, right? So I just plug in 3 and go to the calculator there, I'm getting roughly 5,836 mosquitoes then after 3 days have gone by. Okay, now the population is going to continue to grow, of course. But part B says, when will the size of the colony double? Okay, so we started with 1,000 mosquitoes. Like, how long are we going to have to wait until we get to 2,000 mosquitoes? Well, it's going to be less than 3 days, right? Because at 3 days, you're already at more than 5,000 mosquitoes. So P is the population. I want to set the population equal to 2,000 mosquitoes and then solve this equation for T to figure out the time that it will take to get to a population of 2,000 mosquitoes. Let's solve this equation. If you divide both sides by 1,000, 2,000 over 1,000 is 2. And 2 equals e to the power 0.588 times t. The bases are not going to match there nicely, so I'll want to use logarithms next. Take the ln of both sides. That allows the power to come in front of the logarithm there on the right. So you're going to have 0.588t times the ln of e. The ln of e is 1. And then you'd want to divide both sides by 0.588 to get t all alone. Go to the calculator. ln2 divided by 0.588 would be roughly 1.18 days if you go nearest 2 digits on that. Okay, so that's how long somebody would have to wait to see the population double from what it originally was there. Part C, when will the size of the colony be 10,000? Okay, well again, P is the population, right? So I would just simply set the population equal to 10,000 now and solve for T. Divide by 1,000. 10,000 over 1,000 is 10. And so now I'm looking at 10 equals e to the power 0.588 times t. Now if I compare this equation to the one that was right above there in part B, I'm solving. The only adjustment is going to be at the end, where I see ln2, it's going to be ln10. So if I go to the calculator now and type in ln10 divided by 0.588, I get roughly 3.92 days as the answer. Okay, let's take a look at one more. Problem 16 is another exponential growth situation. It says, according to data listed at www.census.gov, the world population was approximately 6.04 billion people at the beginning of 2000. It has been estimated that the population in billions is growing exponentially according to the function p of t that's given there. All right, part A, what will be the world population at the beginning of 2020? So t is the time that, more specifically, it'd be the number of years since 2000. Well, in 2020, it would have been 20 years since. And so I would want to just plug 20 into the formula there where I see t and then go to the calculator. If you do that, you should be getting roughly 8.3 billion people would be estimated in the world during the year 2020, this year. Okay, and let's take a look at part B. It says, some demographers believe that 60 billion people is the maximum for which the planet can provide adequate food supplies. How long will it take the world population to reach that amount if the trend continues? Well, okay, so the population is represented by P. I'd want to set that to be 60 billion. I'll just let it be 60 and just keep in mind that, I'm working with billions here. Solve for T. And, okay, if you divide both sides by 6.04, 60 divided by 6.04 would actually be an infinite decimal, so to have this be more exact, I've kept it in fractional form. The bases won't match up nicely, so we'll want to take the ln of both sides. I've done that on the next line. That allows me to pull the power in front of the logarithm there on the right. The ln e is 1. It seems like we're doing the same thing over and over again in these problems. To get t all alone, then divide by 0.016. When you go to the calculator then and type in ln of 60 over 6.04 all over 0.016, I was getting roughly 143.5 years. Okay, so roughly in the year 2143, 2144, if the trend were to continue, we would reach a population of 60 billion people in the world. And some people believe that that's a big problem. Now, the rate, this is of course, the exponential growth model, okay? But the rate is always changing. I mean, this model here is from the year 2000, okay? And the growth rate of the world at that point was 1.6%. Now, I doubt that that is the same. It's probably around that number right now, but it has been 20 years since, and a lot changes in 20 years. So to make, to have this be more exact, like we'd probably want to update the model and, see what it looks like, if we understand that things are always changing there. So that's all I had in this worksheet that I wanted to show you. I thought that I would save all the other problems that we didn't look at for you guys to look at on your own there for just, just some more practice. Now, there was some population growth and decay problems that were in the book, and I did assign a few of those, but this is just some more applications, I guess you could say. Some of these were actually in the book. Some of them were from other sources, though, too. I've got the answers all at the end of this worksheet here, so you can check the end to see if you're correct with the calculations. And so at this point, we are now done with Chapter 5, and we'll plan to get into Chapter 6 next.